All right. So today's video is going to be about reactions of acid chlorides and acid anhydrides. So just a quick overview of each of those things to begin with. Both acid anhydrides and acid chlorides are derivatives of carboxylic acids, and that we talked about in our last video. So acid anhydride is an organic compound, obviously, and it consists of two acyl groups bonded to the same oxygen. So kind of think esters when you think that. And these molecules are quite reactive, so they're very widely used in the industrial chemical field, and they can be used to prepare acetate esters and lots of different resins, polymers, and different things. And then in nature, these molecules are involved in many different reactions. They can react with nucleophiles of different cellular components. For example, at the surface of certain bacteria like Neisseria meningitidis and other different things. And then here we have acid chlorides, and they're also a derivative of carboxylic acids. They're very reactive and very versatile. In fact, they are the most reactive out of all of the carboxylic acid derivatives. They're useful for making amides, esters, and anhydrides, particularly because chloride is so electronegative. It has those interesting properties. Again, both of these two things can be hydrolyzed to create carboxylic acids, as we saw in the last video. And yeah, that's about it for that. So we'll go into some of the different reactions of each of these, and we'll go ahead and start with acid chlorides just because there are so many of those. Acid chloride reactions are so numerous that I thought it would be easiest to kind of break them down into three categories. And then I'll go ahead and write out the mechanism for one reaction from each category. So to begin, the first category of acid chloride reactions occur with oxygen nucleophiles. So these include nucleophiles like water, hydroxide, alkoxide ions, and hydrogen peroxide. So these reactions produce products like esters and anhydrides. The next class of acid chloride reactions are done with nitrogen nucleophiles, and these include ammonia and hydroxylamine. These reactions result in exclusively amide products. And then finally, carbon nucleophiles are the last class, and they use reagents like organometallic reagents and organolithium reagents. So organometallic reagents are similar to like the Grignard reagent, and acetylides are also used here. And these result in like ketones and different carbonyl products. So I'll go ahead and draw a reaction with an oxygen nucleophile now. This reaction is going to show the conversion from an acid chloride, which I forgot to mention is also sometimes referred to as an acyl chloride. But anyway, we're going to go from an acid chloride to an ester. So we'll start with kind of a generic acid chloride, just so you can see how this applies to just about any acid chloride. So there we have that. And then the first thing that's going to happen during this reaction is a protonation step. So here we have just kind of a generic alcohol. And we're going to see, or I'm sorry, I misspoke, but this is going to be a nucleophilic addition. So you're going to see that this adds right here, because this is your oxygen nucleophile that we've been talking about. So this would be the equivalent of like a hydroxide. And then, so we add there, and then that kicks electrons up to our oxygen up here. There should be 2 lone pairs on that guy. All right, so I'll go ahead and draw the intermediate that results from this step. So there's our water molecule, or sorry, our alcohol molecule that we just added on here. Here's that R group. And now we're going to have a positive charge on this oxygen here. The chloride is still there, just down here at the bottom. And we now have a single bond to our oxygen, which is now negative. Okay, so next we're going to add pyridine to our reaction here. There's that. Those are supposed to be double bonds. Sorry about that. And so the pyridine is going to go ahead and deprotonate that alcohol that we just added on there. So here we can see it doing that. And then I'll draw the product of that. So now we're left with, we still have our chloride. We have an O bonded to some sort of R group. 2 lone pairs on that oxygen here. And we still have our oxygen with 3 lone pairs up at the top of the molecule. So now, what likes to happen in these reactions is that the electrons from the oxygen like to kick back down into the rest of the molecule. So that's exactly what we're going to see happening here. And then those electrons are going to go ahead and kick off chlorine because it's a pretty good leaving group. So then after that chlorine is expelled, I'll show that here, we end up with kind of our generic ester. So we can see that oxygen bonded to another R group, which is so characteristics of the esters that we typically see. So that's just one example of a mechanism that goes along with the oxygen nucleophile section of reactions of acid chlorides. So as you can see, there are tons of different kinds of oxygen nucleophiles, which means there are so many reactions with acid chlorides and oxygen nucleophiles. Next, I'm going to go through a reaction with a nitrogen nucleophile. All right, so just like the reaction with our oxygen nucleophile, we're going to go ahead and start with an acid chloride. We'll do the generic version. Obviously, this can happen with a bunch of different kinds of acid chlorides, but just for versatility, we'll keep it pretty general here. So we're going to start by seeing an acid chloride react with a first degree amine. So that would be, if you remember, the amine or the nitrogen of the amine is only bonded to 1 carbon and 2 hydrogens, and it still has a lone pair. And we'll have lone pairs up here. Okay, so then that lone pair from the nitrogen is going to go ahead and it's going to be another nucleophilic addition onto that central carbon, which kicks electrons up to our oxygen, breaks that double bond. Very similar mechanism to what we saw with the oxygen nucleophile. So then that amine is going to add onto that central carbon here. Just draw that out. We'll have our R group. And then at this point, the chloride is still also bonded to that central carbon. We have a single bond now to our oxygen and 3 lone pairs and a negative formal charge. And then the next step is another addition of that primary amine. So if we were to write this out, it would be 2 equivalents of, or at least 2 equivalents of that primary amine. Some of these reactions have up to 5 equivalents of the amine that are required to make the reaction happen. So that's good to keep in mind. All right, so we're deprotonating that hydrogen that's attached to the amine. And then here we are, passing those electrons. So the result of that is the loss of that hydrogen atom. Chlorine is still here. And we have our oxygen with its 3 lone pairs. Okay, and our nitrogen is no longer positive. That's good to note as well. So now same thing's gonna happen as last time, where the oxygen's gonna kick those electrons down into the rest of the molecule. And that extra flow of electrons is going to cause that chlorine to be expelled. And we'll see again that we lose that chlorine, leaving us with our second degree amide, which again, just for review, is characterized by a nitrogen bonded to only, or to actually this time to 2 different R groups or carbon molecules. So we can see that here. So again, this is just one example of the many different reactions you can do with nitrogen nucleophiles and acid chlorides. Of course, this one is using an amine, a primary amine as the reagent, but these can also be done with ammonia and other different types of amines. So I'll get this erased and we'll go on to carbon nucleophiles. The reactions of those acid chlorides with carbon nucleophiles tend to get a little bit, they seem a little bit more complex. So the one we're going to look at is an acid chloride so for this one, I'll do a slightly more specific example, but we'll do an acid chloride with the Gilman reagent, which if we remember, that's the lithium cuprate. So it's an organolithium reagent. So we'll just draw that out. So here we have our acid chloride that kind of looks like an R, it's supposed to be an L. And here is our organolithium reagent. So as you can tell, that copper is not bonded to the lithium. They're just strongly coordinated because of those differing charges. So what's going to happen here is that we'll start with a nucleophilic attack, same as the last ones. This time it comes from the bond to the R group to that central carbon. We know the drill at this point, kicks electrons up to our oxygen. Next, we're going to see the formation of an alkoxide. So our chlorine is still there. We have added that R group from our organolithium reagent. We've broken the double bond to our oxygen, which is now negatively charged. So on this one, a lot happens at once. So those electrons kick down to the lower part of the molecule, and they actually, since chlorine is such a good leaving group, they just kick it off right away. And then following the expulsion of chlorine, we have our ketone. And it's important to note that this is where the reaction will stop, because the ketone can no longer be attacked by our organolithium reagent. So those carbon nucleophiles, I think they look a little bit intimidating just because they're different from the other the other nucleophiles, but they occur again with those organometallic reagents, organolithium reagents, and acetylides, and they result in tertiary alcohols and ketones. So just quick review before we move on to acid anhydrides. Oxygen nucleophiles are listed here and result in esters and anhydrides as products. Nitrogen nucleophiles leave you with amide products. And then our carbon nucleophiles are those tertiary alcohols as well as ketones. Okay, so now we'll go ahead and move on to our reactions with anhydrides. Starting out here, it's important to note right off the bat with acid anhydrides that they can perform all the same reactions as acid chlorides. However, they are slightly less reactive, which means that they are not able to form acid chloride. So in terms of reactivity of carboxylic acid derivatives, it goes acid chlorides, acid anhydrides, and then we continue to move down the list. So if we have a functional group that is less reactive than another functional group, obviously we're not going to be able to form the first functional group from the less reactive functional group. So with acid anhydrides, we can form esters through a process called alcoholysis. So basically, we are combining an acid anhydride with an alcohol. And I'll go ahead and draw out that mechanism. Here, we've got our anhydride. Like the last one, we'll keep this general. I just really want to drive home the point because I think it's important, but just to reiterate, acid anhydrides can be formed from acid chlorides with those oxygen nucleophiles. However, acid chlorides cannot be formed from acid anhydrides because they are so much less reactive. So our first step here is going to be a nucleophilic addition, and our nucleophile in this case would be an oxygen nucleophile. So we're adding here at this carbon, kicking those electrons up to the oxygen. Again, very similar mechanism to the last ones we've seen. But now, we kind of have those two carbonyl looking parts of the molecule. So it's going to get a little bit different. Sorry, this one got kind of compressed here. All right, so we still have our R group on the end. We've broken our double bond to the oxygen. Kind of negative charge there. And then we have also added our alcohol nucleophile or our oxygen nucleophile to this very molecule. So there's that, and we can see the R group from that alcohol. It could be ethanol, could be methanol, could be a variety of things. And we do have a positive charge on our oxygen here. So the next thing we're going to add is pyridine. If you notice so far, this is the exact same reaction that we did with acid chloride to form esters. So that makes it nice and easy. These things are very similar. Pyridine is going to deprotonate our product of the nucleophilic addition. That arrow is supposed to be going to the oxygen. Sorry, I got a little bit cramped in there. So here's the product of that part of the reaction. Notice how this left side of the anhydride is completely untouched thus far. So we have our OR here. And our oxygen, still single bonded, still 3 lone pairs, still negatively charged, and our R group down here. So then we're going to see what we've seen so many times before. Those oxygen electrons are going to kick down. This time they are going to pop over here to this central oxygen, and this whole side of the molecule here is going to be expelled. So we're going to lose, in short, we're going to lose RCOO. Which leaves us with our ester. So a slightly different mechanism. Essentially, instead of like forming the ester, we're kind of just deleting half of the molecule and are left with an ester. So this is sometimes called acid anhydride alcoholysis, which is kind of an interesting term. Okay, so next we'll go through a reaction or a nucleophilic addition of acid anhydrides with nitrogen nucleophiles. Okay, so we'll keep the same general anhydride that we've been looking at. And our nucleophile in this situation is going to be a primary amine. Which is indicated by the presence of those two hydrogens and the lone pair, because that means that our nitrogen is only bonding to one carbon. So that is going to go ahead and attack our central carbon for a nucleophilic addition, kicking those electrons up to our oxygen, leaving us with the same thing we've seen. We still have our R group, but we now have our primary amine on there as well. And we have a bunch of bonds on our nitrogen, so it's going to be positively charged. And then we are breaking our double bond on the oxygen, meaning it'll have 3 lone pairs and a negative charge. Okay, so next we're going to add that same primary amine a second time. So that's again important to notice that it does require 2 equivalents of your primary amine. So those that lone pair is going to go ahead and deprotonate our hydrogen from the amine, which results in this intermediate here. So our nitrogen is no longer positively charged because we just have this going on. And we have our oxygen here. Oops. With its 3 lone pairs. And this guy over here. So what we've done essentially by deprotonating that amine group is created a good leaving group so that when these electrons kick down from the oxygen, we can essentially remove this whole part of the molecule, which leaves us with an amide. Once you start getting into the carboxylic acid derivatives, it's really easy to kind of remember these mechanisms because they're pretty much the same throughout. The thing I want to talk about is the reduction of acid chlorides. So we've talked a lot about reducing agents in organic chemistry, but we'll just talk about some of the ones specific to acid chlorides now. We'll have a strong side and a weak side. It's important to note that weak reducing agents for acid chlorides result in the production of aldehydes, and then strong reducing agents create alcohols. So we'll start with strong because there are only a few of them. So one example would be that organolithium reagent that we've talked about. This isn't the same one. We talked about the Gilman reagent, but this is a different organolithium, very strong reducing agent, actually the strongest. And then in the strong category, we have some medium reducing agents. So that would be like palladium on carbon and deuterium, and then sodium borohydride is another mediumly strong reducing agent. And all of these take you from an acid chloride to an alcohol. So I'll just draw that out down here. You'll have your acid chloride here. To an alcohol of some sort. Okay, over here on our weaker end of the spectrum, we have a whole lot more different reagents. So we have another type of organolithium reagent. And that one is called lithium aluminum tritert butoxyhydride. So quite a mouthful. It's kind of a trippy looking molecule. I'll try and draw it out here. So we have our aluminum in the middle. And it's important to remember with those lithium reagents, the lithium is not typically bonded to like the central molecule of the reagent. It's just coordinated to it. So we can see our tert part of the tritert butoxyhydride. And then we'll have our coordinated lithium atom. Lithium's positive, aluminum's negative. There we go. And then we also have a type of reduction called the Rosenmund reduction, which is that strong, like the medium strong palladium on carbon and deuterium catalyst. But then what you do is you actually poison the catalyst with quinoline. So that means the reaction doesn't go all the way. Sorry, I misspoke. It's not the palladium on carbon, it's deuterium. It's palladium on deuterium. And then you're poisoning it with quinoline, which looks like this. And so poisoning the catalyst, all that means is that you're kind of essentially controlling where the reaction stops. So instead of allowing it to go all the way to an alcohol with that strong reducing agent, we're stopping it at an aldehyde. So here is your quinoline that you would be poisoning your catalyst with. And then, oops. Lastly, we have a very commonly used reducing agent, which is kind of commonly known as dibal-H, but that stands for diisobutyl aluminum hydride. And just quickly, here's what that guy looks like. We got our aluminum here, bonded to a hydrogen. Just like that. So again, all of these are weak over here and they start at an acid chloride. Use any of these weak reducing agents and you end up with an aldehyde, which is our carbonyl group and then a hydrogen bonded to that central carbon. So I hope you've learned a little bit about the versatility of these acid chlorides and acid anhydrides, because there are plenty of reactions to choose from, and they're very useful functional groups.